I'll call this little video force components. And what we're looking at here is the fact that you can break down forces into components. We already saw a little bit of this with velocities. Remember that projectile velocity? And we broke it down into a horizontal component and a vertical component. Called that one VV and that one VH. Do the same with forces. Now, obviously, if the gravity on an object is acting straight down, Fw equals mg. I say Fw because this is weight force, mg. Gravity is just the acceleration, or g is the acceleration. You have to multiply it by the mass to actually get the force acting on the object. Now, let's have an example. When you've got a slope, and you've got a box or something sitting on the slope, then m is indeed acting straight down like that. But we now want to know how much of that force is directly into the ramp and how much is down the ramp. Now the down the ramp's real easy. We just draw a little line like that, dot, 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 dot. And when we get to a point that we can make a right angle, we stop. So we've now broke that vector into two vectors. We've broken it into a force vector parallel to the ramp, and we've broken it into a force vector perpendicular to the ramp. Why is that useful? It's useful for two reasons. It's the force vector parallel that will accelerate the block, right? And it's the part of the vector that goes into the ramp that the ramp pushes back. If you push into a ramp this way, it pushes back with its support force. So the support force is just equal to the component that pushes in. So that will be equal to the support force. So if I want to put numbers on that, I know that this angle, theta, of the ramp is the same as that angle there. The angle between the perpendicular, there, and the vertical. Perpendicular to the ramp and the vertical. If you don't believe me, you can just have a little look at this diagram and have a little think. There's a few things that should tell you that this is the same. For example, that's alpha, right? Where's the other alpha? The other alpha is this one here. And this little triangle, alpha, that little triangle there. See it? So if that's alpha, that's 90 degrees. Alpha, 90 degrees. The other one, theta, must be right there, right? So that's theta. That means F parallel must be weight force, Fw, times the sine of theta. So this one is F sine theta. Whereas the other one, as you'll imagine, is F cos theta. So what we've done is we've broken a vertical force into two components. We often need to do that. I'll give you another example. Maybe this time we've got a block and someone's pulling on it with a rope, and this is 30 degrees. Maybe they pull on it with a force of 100 newtons. Now again, I can't just sit here and go, I use 100 newtons to work out the acceleration, because if this block has a mass of that, then F equals ma. Alright? But there are different components here. Alright? Now there's a whole bunch of forces acting on this, but let's just say that this force can be broken into two components. We can always break vectors into other vectors. So the vector 100 newtons has a vertical component and a horizontal component. So if I want to know the horizontal acceleration, I need to use the horizontal component. Right? So F equals ma is the formula, but what's the horizontal force? So we've got a horizontal force, which will be 100 times the cos of 30 degrees. Whereas, so that's the horizontal force. Force vertical will be equal to 100 times the sine of 30 degrees. So one of the horizontal acceleration, I have to just use the horizontal force, because a vertical force doesn't produce any horizontal acceleration. So we've broken up this vector on an angle into its components. This is often done, and it's very useful. I think that's probably given you enough of a look to see what's going on.